lead a session just to show you guys the program Polymake. I told you about Polymake, which is a program that is very useful for doing all kinds of computations with polytopes. And he will just show you how it works, answer any questions that you might have. By the way, if anybody has used Polymake and has installed it and would like to talk to him about it, he actually is installing the new version right now, and so.
If anybody's actually managed to install the new version, I would like you to talk.
Yeah. Polymake is a wonderful program that is a little bit too difficult to install. So I think the hardest thing is to install it, and then after that, it's pretty simple. And one thing that he's going to do is tell you, maybe he'll take a few minutes to just tell you a little bit about his research. So his research is also on polytopes, and he might tell you a thing or two about what he does, and see if maybe you guys are interested in working with him a little bit with it. Okay. So what I want to do today is talk about the Farkas Lemma. And if you've looked in the book, you've seen that there are several versions of the Farkas Lemma, and I want to discuss as many as I get to. These different statements are statements that are logically equivalent to each other, but somehow they're kind of different psychologically. So we'll talk about them. Okay. So I'll start with where I was last time. We're going to start by proving the Farkas Lemma number 4. Okay? And you'll notice that I'm doing this a little bit differently from how the book does it, which is why I'm starting with number 4. If you're interested in going from 1 to 2 to 3 to 4, then the book does it that way, but I'm going to go in a different order. So we're starting with matrices V, Y, and X, and I forgot to write the dimensions, so this is a D by N matrix. This is a D by M prime matrix. And this is a column vector, D by 1. So either there exists 1 by N row vector T and a 1 by M prime vector U, such that X equals VT plus YU. And remember that what we're thinking is that X we want to write as a combination of the columns of V, and T tells us what the coefficients are. This is why it's useful to draw it in this way, so that you see that this length is the same as this length, and so we're talking about the coefficients of T multiplying the column vectors in V. Okay? So X is a combination of the columns in V plus a combination of the columns in U, where the sum of the coefficients in T is 1, and both T and U are greater than or equal to 0. Okay? And I pointed out to you last time that what we're saying here is that X is in the polytope given by the convex hull of the vectors in V plus the cone of the vectors in Y. Okay? So I'm saying either the point X can be expressed in this way and therefore is in the polytope, or there exists a row vector 1 by D A and a number alpha, such that the dot product of A and VI less than or equal to alpha. And here VI's are the columns of this matrix, right? So we're calling this V1 up to Vn. So the dot product of A with all the columns is less than or equal to alpha. The dot product with these guys is less than or equal to 0. And the dot product with X is greater than alpha. Okay? And let me remind you what I said last time also, which is that we now have this great main theorem for polyhedra, which says that I can describe my polytope P either in its V description or in the inequality description. Okay? And so what I said basically is that, I mean, this is the mathematical statement, but the translation and the way that you should really think about this is that either x is in the polytope or there exists some inequality that explains why x is not in the polytope. So or let me say x does not satisfy one of the inequalities that P satisfies. But not both. Either or, but not both. Okay. And so if I say it in this way, then I think this is a much more natural statement that makes more sense. Okay. So we're going to go ahead and prove this statement. And really, what I need to prove is basically that this translation is correct. Okay. So, proof. Yep.
You're saying that x is either in the polytope or not. Is P a polytope or a polyhedron?
Sorry, I keep, and it's probably going to keep happening that I confuse that I'm careless about whether to say polytope or polyhedron. In this case, I mean polyhedron because this thing could be unbounded. Yeah. So I'm saying basically either x is in the polyhedron or not, and therefore some inequality shows that. So here's the proof. Let's say that x is in the polyhedron. Okay. I'm going to do two cases. Either it is in or it is not in. So if x is in the polyhedron, then consider A and alpha such that A dot vi is less than or equal to alpha, A for all I, and A dot yj is less than or equal to 0 for all j. Okay. So what am I doing? I'm saying suppose x satisfies this first condition. I'm going to prove that it doesn't satisfy this condition. So I'm saying consider an A and an alpha such that A dot vi is less than or equal to alpha and A dot yj is less than or equal to 0. What I'm going to prove is that then this cannot be satisfied. So let's prove that. Okay. Because x is in P, I can write it in this form, right? As T1 V1 up to Tn Bn plus U1 Y1 up to Un prime Yn prime. With the sum of the ti's equal to 1, the ti's greater than or equal to 0, and the uj's greater than or equal to 0 by definition. Right? And then let me just compute the dot product of A and x. Okay? This is the dot product of like this. Right? And remember that here the ti's are constants and the a's and the v's and the y's are vectors. Okay? So let me pull out these constants. T1 times A dot V1 plus up to Tn times A dot Vn plus U1 times A dot Y1 up to U n prime times A dot Y n prime. Just moving stuff around, okay? And now I'm going to use this hypothesis that A dot Vi is less than or equal to alpha. Okay. So A dot Vi is less than or equal to alpha, and T1 is greater than or equal to 0. And therefore, this is less than or equal to T1 times alpha. So on, Tn is greater than or equal to 0, and this is less than or equal to alpha, so I get Tn times alpha. Okay. And what about these guys? Well, each A dot Y1 is less than or equal to 0, and U1 is greater than or equal to 0. That's what I have here. So therefore, this is less than or equal to 0, and all of these are less than or equal to 0. Okay. So what I get is T1 up to Tn times alpha. And now because the sum of the Ti's is equal to 1, then I get alpha. Okay. So what did I prove? I proved that the dot product of A and X is less than or equal to alpha. In other words, I'm proving that the second condition isn't satisfied, right? I assumed A, and I proved not B, because I said if this condition is satisfied and this condition is satisfied, then this one is not satisfied. So I've done one direction. I've proved that if A holds, then B doesn't hold. Okay, we're good so far? For the other one, let's assume that the first one doesn't hold, and let's prove that the second one holds. Okay. Do you guys have a question? I said that A dot Yi is less than or equal to 0, and Ui's are greater than or equal to 0. So this is what I have here and here. So if I multiply a positive number and a negative number, I get a negative number. So it's not equal to 0, it's less than or equal to 0. Okay. So that proves the first direction now. Let's prove the second direction. So let's assume that X is not in P. Okay. So if X is not in P, then because P has an inequality description, X must violate one of those inequalities. Okay. So then X violates some defining inequality of P. So let's say that this inequality says, so in other words, so let's say that inequality says A dot P is less than or equal to alpha for P. Okay. So I'm assuming that this is the linear inequality that is satisfied by the polyhedron, but not satisfied by X. Okay. This is the inequality that X violates. Okay. So now I'm going to say the following thing. I'm going to say each V sub I can be written, each V sub I is in the polytope. So let's think about why that is. Because the polytope is the convex hull of V plus the cone of Y. Okay, it's the things that I can write as something here plus something here. Now, V sub I is one of the points in V, so V sub I is here, and 0 is in any cone. Right? So V sub I plus 0 is in P. So because V sub I is in P, then by what I have there, I have that A dot V sub I is less than or equal to alpha. Okay, so that's one thing. Now, the other thing that I want to point out is the following, that if I take V sub I plus any positive multiple of U sub j, so lambda is any positive number, then this is in P. For the same reason, because this is in the convex hull of V, and this is in the cone of U. Any multiple of Uj has to be in the cone. Okay? So because this is the point in my polyhedron, it must satisfy that inequality satisfied by all points in the polyhedron. Okay? So that looks like this, which I can rewrite as A dot Vi plus lambda times A dot Uj less than or equal to alpha. Okay? Now, if you think about this, this is just some number, A dot Vi. It has some value. But I'm saying that this inequality holds for any positive lambda. Any lambda greater than 0. Okay? If A dot Uj was positive, then I could multiply it by an arbitrarily large lambda and make it as big as I wanted it to be. Okay? So the only way that this could be less than or equal to alpha for any positive lambda is if this thing that I'm multiplying it by is negative. So that when I multiply by really big things, it's becoming really negative instead of really large. Okay? So that means that A dot Uj has to be less than or equal to 0. Okay? And if you look at what I proved that there exists an A and an alpha which satisfy this, this, and this. And these are exactly the three conditions that I have in my thing that I called B over there. Okay. So that concludes my proof. Any questions about it? Okay. So you see this proof is not too difficult. It fits on one set of boards. And again, let me point out the very important fact that all the difficulty of this proof is in the work that we already did. We already did the hard work of proving the equivalence of the V and H descriptions, and that's really what allows us to write this proof, and it's a sharp proof. Okay? And actually, this is the reason that I wanted to prove Farkas Lemma 4 first. So if you look at the book, he proves Farkas Lemma 1 first, and he doesn't use the main theorem for polyhedra, and you'll see that his proof is more complicated than what I'm doing here. So that's Farkas Lemma 4. Okay? Any questions about it?
Relative to V, I guess specifically V, but V and Y, the relationship of A and alpha to that? I mean, we're just looking at this thing exists, but how might they be related to our actual convex hologram stuff?
So the question is basically, where do A and alpha come from in relation with these other things? And the answer is basically that it comes from the translation between the V description and the H description. So V and Y give us our V description of the polytope, of the polyhedron. And if you want to find out this kind of, if you want to find an inequality like this, then you're in the territory of the H description, where you want to describe the polyhedron by inequalities. Okay, and so the A and alpha are basically something that you would obtain when you translate from the V description to the H description, and that's where the inequalities come from. So it kind of comes down to the same computational problem of how do you go back and forth between H and V descriptions.
Are there unique comparisons?
Yes. Yes. Oh, not A and alpha. The H and V descriptions are unique, but if you think about what this is saying either a point is in the polytope or it violates an inequality, but it could violate several inequalities, and that's the reason why this is not a unique A and alpha.
I meant was is each alpha unique to each A?
For each A, there's kind of a smallest alpha. Yeah. If you violate an inequality, then you can kind of push the right hand side of the inequality to the smallest possible violating place. Okay. So that's Farkas Lemma 4. And you see from this proof that it's more or less equivalent to the H and V description equivalence. Okay. So now I want to talk about Farkas Lemma 2. Okay? And again, first I'm going to write a statement that looks kind of like this, and then we'll see what the statement actually means. So consider some matrix A and some column vector Z. And let's say that this is m by d, and this is m by 1. Okay. Then either there exists a column vector x such that ax equals z and x greater than or equal to 0, or there exists a column, a row C such that CA greater than or equal to 0 and CZ less than 0, but not both. Okay? And what did I say? This is d by 1, and this is 1 by m. Okay. So let's think about what this statement is saying. What we have here, this first condition, is basically an equation like this. Ax equals z is just a system of linear inequalities, linear equalities, right? So a system of linear equalities for x. So it might be something like, I don't know, x minus y equals 2, and 2x minus 3y equals 5, I don't know. Actually, I'm trying to craft a useful, just a second. So maybe this is an example of a system of equations like what we have here. Okay? And we're looking for a solution to this system of equations with the variables being greater than or equal to 0. Okay? So I'm giving you a system of equations like this, and I'm asking you, is there a solution greater than or equal to 0? Can you tell right away from looking at that whether there is or there isn't a solution greater than or equal to 0? You can tell? How? Maybe you can, I don't know. I mean, one thing you could do is just, you know, this has a solution, you compute it, and then you see if it's positive. But actually it turns out that you don't have to work so hard if you just have the insight of saying, what happens if I add these two equations? If I add the two equations, then I get, oh, I meant this. I meant this system. If I add these two equations, then you get this. And then you say, well, this obviously cannot have a positive solution because, you know, this is positive and this is negative. This is what the Farkas Lemma says. It says either there exists a solution which is positive, or there exists, this you should think of as a linear combination of the rows of this matrix. Right? So a linear combination of these equations gives you a left-hand side greater than or equal to 0 and a right-hand side less than 0. Okay, so let me say translation again. Either a system of equations has a solution greater than or equal to 0, or some combination of the equations, some linear combination of the equations gives something like a1x1 plus dot 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 plus anxn equals b, where all the coefficients are positive and the result is negative. Okay? In other words, if the system doesn't have a solution, then there is a one-line proof. That one line being, you know, take my equations and give a combination that looks like this. Okay? There's a very clear reason why we cannot solve the system. So if you're teaching, if you're one of these CM² fellows that has to go into the middle schools and high schools and teach them about systems of equations, it's actually something that it could be useful for them. You know? In Math 60 also. I mean, this is really a very basic fact, but you'll see that actually it's not so easy to prove. But now we did all the work and we can prove it. So how do we prove this Farkas lemma number 2? We're just going to show how it follows easily from Farkas lemma number 4. Okay. So what am I going to say? I'm going to say there exists an x such that ax equals z and x greater than or equal to 0. If you think about what that means, this means exactly that z can be written as a non-negative combination of the columns of A. When you take a matrix A and you multiply it on the right by a column vector, then let's do it over here. If you take A and you multiply by a column vector, then what you're doing is just taking a linear combination of the columns of A. And the coefficients are given by this. And again, you can see that just from the shapes. This is size D, this is size D, so that's the way the multiplication goes. So what this is saying is just that Z is a non-negative combination of A. And we have a name for that, that's just the cone, right? This is the same thing as saying that Z is in the cone of A. And this is beginning to sound like the first part of Farkas Lemma 4. Okay? But in order to be in that, we need to take convex hull of something plus cone of something. Okay? And then I'm just going to do this trick where I can just say convex hull of the point 0 plus the cone of A. Okay? 0 is a point. It's a polytope. It's a very boring polytope, but it's a point. And then when you look at this Minkowski sum, its elements are 0 plus whatever is here. So that silly little trick allows me to use Farkas Lemma 4. Okay. Now, okay, so basically what I just did is that I took this statement and I showed that it is equivalent to this statement if V is this very silly polytope that is just 0. And so probably what I should do then is just translate this into this. So let's do that. There exists a C such that CA greater than or equal to 0 and CZ is less than 0. Well, this is the same thing as saying that there exists a C and an alpha such that I'm just going to write this as C times each A J. So saying that C times A is greater than or equal to 0 is saying that C times each one of the AJs is greater than or equal to 0. C times Z less than 0. I'm just going to write this and then so I'm saying, I mean, let's just do both directions, okay? If this happens, then CA greater than or equal to 0 implies that C dot AJ greater than or equal to 0. And C dot Z less than 0 means that I can find an alpha such that Z dot Z is less than alpha, and alpha is less than or equal to 0. I'm not really saying anything there. And let's do it the other direction. If this holds, then because C dot AJ greater than or equal to 0, then CA is greater than or equal to 0. And if C dot Z is less than alpha, and alpha is less than or equal to 0, then C dot Z is less than 0. So this is a pretty empty statement. I'm not really saying much. And the only reason that I bothered to write it is that I want it to look like what I have over there. Okay? Because if you think about it, we're talking about applying the Farkas lemma when V consists of just the 0 vector. Okay? So I want A dot 0 to be less than or equal to alpha. And that's why I put C dot 0 greater than or equal to alpha. So just think that this is my V sub I. And then you'll see that the statement that I have here is the same statement that I have over there. Yeah. These inequalities are the same as these. Almost. Are they exactly the same? These three inequalities and those three inequalities over there? I mean, of course, you should think that when I say V, I mean 0 there. When I say Y, I mean A there. When I say X, I mean Z there. Is there anything else? I see you guys kind of going like this. So they're flipped. So how do I unflip it? I can just say, where I see A, think minus C. Just put a minus in front of everything over there, and that's going to flip all my inequalities. Okay. And that does it. So that shows that this is equivalent to this when V is equal to 0, 0, 0. Okay. And so in effect, what I'm saying is that Farkas lemma 2 is just a consequence for free of Farkas lemma 4. Okay. And again, the proof is just kind of keeping track of symbols. I'm not really saying anything intelligent here. But what I hope you will agree with is that the statement seems very different psychologically. Here, we were talking about the equivalence of H and V polytopes. And here I'm saying something that seems different. It's about finding a solution to a system of equations that is greater than or equal to 0. So the point is that these statements are more or less equivalent to each other. Okay. Any other questions about Farkas lemma 2? Okay. So now what I want to do is forget about Farkas lemma 4 for a second. And we're going to discuss another one, which is Farkas lemma 3. No, we're going to do Farkas lemma 1. And it says the following. So it starts out very similar. Okay, so we consider A and Z of the same shape. Okay. But now, what I want to do is this. Either there exists an X of size V by 1 such that AX is less than or equal to Z. Okay. So you see that this statement is very similar, but what I had here was a system of equations where I wanted a non-negative solution. And what I have here is just a straight up system of inequalities. So I want to figure out if there exists a solution to a system of inequalities. And I'm saying either it exists or there exist a C of size 1 by m such that C greater than or equal to 0, CA equals 0, and CZ less than 0. And let's see what this means. So let's now take this thing and translate it, and I'm going to use the same box because it sounds very similar, right? Okay. So I'm saying either a system of, now it's not equations but inequalities. Either a system of inequalities has a solution like let's do a very stupid example. So here's a system of inequalities. Why does it not have a solution? Well, because if you add them, you get 0 less than or equal to minus 1. And what Farkas Lemma 1 tells you is that it's that simple. If a system doesn't have a system of inequalities, it is because it boils down to 0 less than or equal to minus 1, period. Or, so I'm saying that now you don't even get coefficients. You really get zeros. 0 times the first one plus, like this, less than or equal to some number b, which happens to be less than 0. Okay. So you see what I'm saying here is that the left-hand side of my system of inequalities gives me all zeros. I get 0x1 plus 0x2 up to 0xn. And what I'm saying here is that the right-hand side is negative. What am I saying here then? C greater than or equal to 0. I didn't have that condition over here, and I have it over here. So why do I need that extra condition? But you see that one thing that I think is always hard to keep track of is are these numbers, are these vectors? So what are they? So C is a vector, okay? And the thing with vectors is that you shouldn't think of them as being positive or negative, because most vectors are neither positive nor negative in this sense. You see what I mean? For a vector to be positive, all the entries have to be positive. For a vector to be negative, all the entries have to be negative. Generally, vectors are neither positive nor negative. So that's why I don't want to quite talk about C being positive or negative. But why do I want these numbers to be positive? The thing is, remember that what I'm describing here is a linear combination of my inequalities. Okay? And this is something that you tell your Math 60 students. If you're going to have a system of inequalities and you're going to multiply by something, that something better be positive or you're going to mess up. And that's what I'm saying here. I'm saying the coefficients that you use better be non-negative so that none of these inequalities get reversed and I lose track. Okay? I force all the coefficients to be positive, to be non-negative. And so what I should say here is that some non-negative linear combination of the inequalities gives this. And so again, what this says is, if a system of inequalities doesn't have a solution, then you have a one-line proof, which is, look at this linear combination and show that it's 0 less than minus 1. That's the only reason why a system of inequalities can not have a solution. Okay. Strictly positive, you mean? So surely C has some entries that are positive. Yeah.
I see. So when you say greater than or equal to 0, you mean some of the entries can be 0.
Yeah.
I got you. Okay.
Okay, so what I'm going to do is, again, prove that the lemma 1 follows from the lemma 2. And this is kind of a fun proof, actually, so I'm going to... So let's do that. There exists x such that ax less than or equal to z, if and only if what? I'm just going to do a big chain of if and only ifs. Okay. This is true if and only if there exists x and y such that ax plus y equals z and y bigger than or equal to 0. Okay. We did the same trick last time. If z is bigger than or equal to ax, then let's subtract them and call the result y. That y is greater than or equal to 0. Okay. Now I'm going to do something that is going to seem strange. What I'm going to do is I'm going to say, take my x, okay? And x, like I said, x is a vector. It's probably neither positive nor negative, but I can write it as something positive minus something positive. Let me say it this way. U plus minus v, where u basically is the positive coefficients and minus v is the negative coefficients. So I separate the vector into its positives and its negatives. Okay. So what I get is that there exists u, v, and y such that a u plus a times minus v plus y is equal to z, and u, v, and y are bigger than or equal to 0. Okay. And then I'm going to write this in matrix form like this. A minus A identity times U V Y equals Z. If I multiply this matrix times this matrix, I get A times U plus minus A times V plus identity times Y. So I get this. Okay. So I told you that these steps should seem strange, but you see what I accomplished is I accomplished to rewrite what I had as a system of equalities where the arguments should be greater than or equal to 0. Okay. And so now this puts me in a position to apply Farkas Lemma 2, which says that this is true if and only if it's not true that there exists a vector C with, let me multiply it like this, C times A minus A I greater than or equal to 0, and C times Z less than 0. This is what Farkas Lemma 2 says. This is true if and only if. It's not true that, you see, when I multiply these blocks, this is just CA, C minus A, and CI. So what I get is that there exists C such that CA greater than or equal to 0, C times minus A greater than or equal to 0, C times the identity greater than or equal to 0, and C times Z less than 0. You have to be a little bit careful about how this stuff multiplies out, but you'll see that if you look carefully at the sizes, you'll see that this is really how this multiplies out. This block times this block, this block times this block, this block times this block. And that means that there should not exist a C such that, you see what I'm writing here is CA bigger than or equal to 0 and CA less than or equal to 0. So that magically becomes CA equals 0. Then CI is just C because I is the identity. And CZ less than 0. And those are exactly the conditions that I wanted in my Farkas Lemma 1. Okay? And that proves the equivalence. Okay? I did this a little bit quickly because I'm running out of time. But I encourage you to look at this a little bit more slowly. But again, you know, if you just kind of step back and think about what we just did is that, again, you can see that there were not really any very deep ideas here. This is just a string of simple observations. And basically what I'm saying is that all these different versions of the Farkas Lemma are equivalent to each other. And the proofs are all kind of little tricks of moving symbols around. But I think the way that you should think about this is that now that we've proved all these things, then you have all these tools that are all called the Farkas Lemma, but that will allow you to prove a lot of things about polytopes. Okay? Whether you're thinking about an HMV description, whether you're thinking about a system of equalities, or whether you're thinking about a system of inequalities. And we'll see that the Farkas Lemma is one of the very